Among the large list of cities in the world under the immediate threat of day zero, the case of Bengaluru is arguably one of the most severe. Home to 14.3 million people, Bengaluru needs 1.3 billion litres of potable water per day but receives only 940 million. The daily consumption is only 65 litres per capita, while the national standard consumption of similar cities is 200 litres per capita daily. Bengaluru Water Supply and Sewerage Board receives revenue on only 51% of the total processed water. 55% of Bengaluru's urban water is drawn from reservoir dams located in the Upper Kaveri watershed. Bengaluru Water Supply and Sewerage Board draws 1,450 million litres daily. Water is transported up an elevation of 500 meters across a distance of 100 kilometers. To manage water resources and prepare for the uncertain future, reliably predicting short and long-term reservoir levels is critical. Utility managers need a decision support system that can help them visualize forecast patterns and prepare risk mitigation strategies. We assembled a cross-functional team to provide a holistic solution to this multifaceted problem. Our plan of action was to understand the physics behind reservoir systems, develop a modeling framework based on a comprehensive feature set, visualize the results into an interpretable decision support system, and disseminate insights and arguments through engaging storytelling. We initially performed a root cause analysis to determine parameters influencing the Krishna Raj Sagara reservoir levels based on previous studies and the given dataset. We found that the given dataset didn't contain all the parameters required to develop a comprehensive feature set, especially weather information, and so we collected daily historical weather data for features like precipitation, wind speed, and humidity, among others. We performed a QA/QC of the compiled feature set to check for consistency, validity, and preparedness for time series modeling. By developing a comprehensive feature set, we ensured that our prediction model is reality driven and of tactical importance to the decision makers. Our modeling journey started with exploring commonly used time series forecasting methods such as the long short-term memory networks (LSTMs), single dimension convolutional networks (CNNs), as well as a seasonally adjusted Facebook profit model. These models work by getting high-level representations of rolling windows of data and then making forecasts of the future. We noticed poor performance in regions of interest, such as predicting reservoir levels during dry and wet weather conditions. As a result, we decided to compare these high-powered techniques against more tried and tested methods like support vector machines, gradient boosted trees, and Gaussian processes. We found that the gradient boosted trees with several engineered features performed best during evaluations and outperformed the heavier deep learning models, not only in terms of predictive capabilities, but with the added benefits of being lightweight, faster, and yielding an interpretable model. This model works by combining several simple rule-based modules to make 90-day predictions. Upon detailed analysis and a comprehensive literature review, we found that artificial neural networks are more suitable for prediction problems involving unstructured data such as images, texts, videos. However, when it comes to small to medium structured or tabular data, decision trees based algorithms are more appropriate. Moreover, deep learning techniques built on ANNs like the LSTMs or CNNs are infamously non-interpretable and fall into the black box models category. As engineering decisions have a major impact on the society, trust in any decision support system is critical. Decision trees, as a collection of if-else rules, are interpretable and therefore can be used reliably in the real world. Our results show that using a simplistic approach such as decision trees can result in a low mean absolute error of 12 feet, which is a prediction accuracy of about 88%. None of the deep learning methods were able to achieve this precision. Our hackathon journey took us further into the mentorship session where we engaged with the BWSSB domain experts whose feedback was extremely crucial. It helped us understand the importance of accurate predictions during monsoons. We decided to weigh our datasets for the months from May to October, representing the high wet and dry weather cycles. This improved the model's 90-day prediction performance from 88% to 94%. In summary, we developed a self-learning water reservoir model, SWaRM, powered by a gradient boosting decision tree algorithm trained to predict forecasts for a 90-day window using historical information. The model is trained based on time series dataset prepared for the Krishna Raj Sagara Reservoir, which contains external environmental data like precipitation, wind speed, temperature, among others, and outflow data from upstream reservoirs Himavati and Harangi in the form of a time series dataset. The self-learning capability of SWaRM is built based on the performance comparisons as the model is trained with live data. For this purpose, a new live model is created with each iteration over the previously trained static model. Comparing the learning and prediction accuracy of static and live models, the better performing model becomes the new static model. The results are pushed to the dynamic and interactive dashboard, and the model performance can be further improved based on future piloting and validation. Our model boasts an accuracy of predictions up to 7 feet, which is equivalent to 94% prediction accuracy for the 90-day forecast. To visualize the results, we created a user-centric interactive dashboard with accessibility in mind. The dashboard is capable of providing short and long-term reservoir level predictions, current reservoir status and historical environmental conditions, as well as summaries of all managed reservoirs on GIS. Let's take a closer look at the forecasts. This chart shows the short and long-term prediction levels of the KRS reservoir. Our dashboard empowers the user to deep dive into the timescale to observe the granularity in the forecasts. Risk mitigation decisions can consequently be taken based on the deviations of the forecast from an adjustable risk level indicator. You will be able to find historical environmental patterns visualized for key influencing factors, which makes it easy to find historical evidence to support your decisions. You can also find geospatial visualizations showing current conditions of all reservoirs managed by BWSSB. This makes sure that you don't get lost finding critical information about your reservoir of interest. Here's what SWaRM can do for you. SWaRM captures dependencies of the reservoir systems comprehensively based on all influencing factors as well as upstream characteristics. You can be sure that the results you get are based on a model that has learned from all possible scenarios. SWaRM has also been trained to capture seasonal wet and dry weather conditions by weighing parameters and balancing datasets. You will be able to rely on the predictions for important seasons like summer and monsoons. In essence, this framework has been configured for maximum scalability while preserving the granularity of pattern recognition along with other user-centric features such as cloud capabilities, differential access, notification systems, and much more. On a broader note, as an asset manager, you will be able to make better strategic decisions to mitigate water shortage or flood risks. As a policymaker, you will be able to make better long-term economic, environmental, and infrastructural policies. As an academic, you can utilize our model as a baseline for future research, and more importantly, as a Bengaluru resident, you will experience affordable and regular water supply. At Team Poseidon, we hope you join us in making a massive impact on millions of lives. Thank you for your attention.